In this video, we will execute complete coverage of air masses, all three front types, and the specific weather sequences associated with each one. This is one of the highest weightage topics in your DGCA Paper 2 exam. Imagine cruising at altitude. You fly out of clear blue skies, and within minutes you are swallowed by solid overcast, rain, and rapidly deteriorating visibility. A pilot who understands meteorology can read a synoptic chart and predict that exact warm frontal sequence before encountering it. Without that understanding, you are flying blind into a hazardous environment. Subscribe to Captain Aero for daily DGCA theory videos. The foundation of all frontal weather begins with an air mass, a massive body of air possessing approximately uniform temperature and humidity profiles throughout. These blocks of air acquire their specific properties entirely from the surface they linger over, which we call their source region. Knowing an air mass's source region allows a pilot to calculate the atmospheric stability along their route long before the aircraft ever leaves the tarmac. This diagram shows the air mass matrix. We classify air masses across two primary variables: moisture on the x-axis, divided into maritime and continental, and temperature on the y-axis, separated into polar and tropical. Polar maritime, or PM, forms over cold oceans. It is cold, moist, and becomes highly unstable as it moves toward the equator, bringing cumulus clouds and frequent showers. Polar continental, PC, forms over cold land masses. It is cold, dry, and extremely stable, frequently producing widespread winter fog and low stratus clouds. Tropical maritime, TM, originates over warm oceans. It is warm, moist, and stable, creating thick layers of low clouds, persistent drizzle, and a high risk of fog. Tropical continental, TC, forms over desert regions. It is warm, dry, and highly unstable during the summer months, throwing up intense dust haze and driving high surface temperatures. These four base profiles dictate the environment you will fly into. They are the difference between navigating a smooth, stable layer of stratus fog or punching through violently turbulent convective storms. Warm front. What is the first cloud type you will see, and at what distance? The answer is cirrus, appearing 600 to 800 nautical miles ahead of the actual front. Looking at this 2D cross-section graph, a warm front is defined by a warm air mass advancing and rising gently over a retreating cold air mass. Warm air is less dense. It slides up and over the cold air at a very shallow slope, approximately 1 in 150. This geometry yields a slow forward speed of 15 to 25 knots. At the highest edge of that shallow slope, roughly 600 to 800 nautical miles ahead of the surface front, high, thin, wispy cirrus clouds form as your first early indicator. Between 400 and 600 nautical miles, the cloud deck thickens into cirrostratus, a thin white sheet that casts a distinct halo around the sun or moon. Dropping to the 200 to 400 mile mark, altostratus forms a thick gray sheet, and light precipitation begins to fall. Finally, 100 to 200 miles before the surface boundary, nimbostratus clouds drop the ceiling, visibility drops, and continuous moderate to heavy rain begins.
Exactly as the front passes, your instruments react. The temperature and dew point rise, the wind veers, and the atmospheric pressure, which had been steadily dropping, suddenly steadies. Because of its shallow slope, a warm front telegraphs its arrival over hundreds of miles, giving a pilot hours of warning time. In contrast, this cross-section maps a cold front. Here, a dense cold air mass advances aggressively, wedging directly underneath a retreating warm air mass. Cold air is heavy. It creates a much steeper slope, 1 in 50, and drives the front forward at 25 to 35 knots. This structure offers almost zero early warning. Immediately ahead of the front, you are flying in the warm sector. Temperatures and dew points are high, often accompanied by low cloud bases and poor visibility. The moment the cold air wedges underneath, it forces that warm air violently upward. Huge cumulonimbus clouds erupt along the boundary line, packing severe turbulence, hail, and intense thunderstorms. As you punch through the front, the instruments swing wildly. Temperature and dew point drop sharply. The wind veers strongly, and the previously falling pressure rapidly spikes upward. Once past the boundary, the sky clears rapidly. You are left with showery cumuliform clouds, brisk winds, and excellent visibility. The dense, steep geometry of a cold front, translates mathematically into brief, extreme violence. This is weather you navigate around, not through. In this zoomed-out cross-section, the mechanics of an occlusion become inevitable. A cold front moves at 35 knots. A warm front moves at 20 knots. Eventually, the cold front catches up. When they collide, the entire warm air sector is violently squeezed and lifted completely off the surface. There are two variations of this collapse. In a cold occlusion, shown here on the left, the trailing cold air is denser and colder than the air ahead of the system. Because the coldest, heaviest air undercuts everything in its path, a cold occlusion takes on the aggressive characteristics of a surface cold front. In a warm occlusion, shown on the right, the absolute coldest air sits ahead of the advancing system. The advancing cold front is forced to ride upward over that denser block of air, causing the system to behave like a standard warm front. Occlusions merge the worst traits of both systems. You face the widespread poor visibility and low ceilings of a warm front, hiding the violently embedded cumulonimbus cells of a cold front. This comparison table outlines the strict exam requirements. Recall the 4 core air masses: polar maritime, polar continental, tropical maritime, and tropical continental. A warm front features a shallow 1 in 150 slope, approaches gradually, and delivers continuous rain. A cold front features a steep 1 in 50 slope, arrives rapidly, and triggers explosive cumulonimbus development. An occlusion occurs when the faster cold front catches the warm front, lifting the warm sector entirely aloft. Mastering the geometry of these frontal systems shifts you from merely reacting to whatever hits the windshield to actively anticipating the atmospheric layout hundreds of miles down your route. Subscribe, Captain Aero. Humidity and stability is next. Link on screen.